All right, we're going to be looking at sequences next, sequences of numbers. And so really we're going to be looking at basically sets or lists of numbers that have a pattern to them. And we're going to be looking at those patterns and learning some interesting things about them. And so just a real basic example of a sequence, one that's very famous one, is just the sequence of squares. 1, 4, 9, 16, 25, and so forth, right? So it's just the sequence of squares. It's a number squared. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. The number that's being squared is the position of the term. And so if that position was, say, n, if it was the fourth term, if n was 4, then you'd be squaring that number and getting 16. So it could be written as n squared, where n is the position of the term. Another interesting sequence might be the sequence 1/2, and then 2/3, and then 3/4, and then 4/5, and so on. And in this sequence you can kind of see that the tops are increasing by 1, the bottoms are increasing by 1, but the bottoms start 1 higher than the tops, right? So you got a 2 instead of a 1, but then they both increase at the same rate. Okay, and so again, if you think about the position being the variable, then here you'd have, this is the first fraction, you have the position is right on top, that'd be your n, and this is just 1 greater. After that it always increases, so this is your n, this is 1 greater, this is your n, this is 1 greater. And so your general form would be the position divided by the position plus 1. Right, so n is your position, so the first term, second term, third term, fourth term, the n is on top. On the bottom, you would have to add 1. So the first term would have 2, second term would have a 3, third term would have a 4, and so forth. Okay. So just some interesting ways to represent some sequences. Now there's tons of really cool sequences. This is one of my favorite sections to teach, and if I was in a face-to-face format right now, I'd be having you guys try a bunch of sequences and just kind of playing around with numbers. I love this. This stuff is cool to me, seeing all the patterns. Even in this squaring one, a pattern that I love, I think it's really neat. You've got the sequence of squares here, but if you notice, going from one to the other, from 1 to 4 you increase by 3, from 4 to 9 you increase by 5, from 9 to 16 you increase by 7, 16 to 25 you increase by 9, and so the increase is a consecutive odd number. The next increase is by 11 to get to 36, and then you increase by 13 to get to 49, and so forth. And so by adding odd numbers together, consecutive odd numbers, you'll always land on a perfect square. It's kind of just a fascinating fact of that sequence. Okay, so sequences, we've got to get sort of a formal definition. The position is very important. The position ends up being your input, and this formula ends up being your output, whatever you get from that. And so a sequence, by definition, is a function whose domain is the whole number. I'm sorry, no, it's the positive integers. Okay, the positive integers. The positive integers being specifically the numbers 1, 2, 3, and so on. Those are the positive integers. And that makes sense because the position represents the positive integer, right? Position number 1 is the first term, position number 2, position number 3, position number 4, and so forth. So the positive integers here, the inputs are representing the position number. Okay. So inputs represent position number. That's really important to remember. Okay. All right. Let's look at going the other way around. So here I had given you a sequence, and I looked at finding a formula. Let's start from the formula and find the sequence. Okay. So just a quick example. How about -1 raised to the n power times 1 over 2 to the n? Now, when we write out a sequence, we often, in a formula, we often use the set notation because the numbers in the sequence make up a set of numbers. Okay, so we just use the set notation to represent a sequence. Now, what I want to do is I want to think about this in terms of inputs and outputs. Let's think of it in terms of an n value, and I'm going to call this maybe a sub n as my output. Remember, with functions we use like that f of x notation. With sequences we use a sub n as a typical notation we would use. So a sub n is then the output. So the n values, again, they're positive integers. So we just start position 1, position 2, position 3, position 4, position 5, and so on. Well, at position 1, you simply plug a 1 in everywhere there's an n. So I would have -1 to the 1, well, that's a negative, and then 1 over 2 to the 1, well, that's a 1/2, so it's -1/2. With an n value of 2, I would get -1 squared, which is positive 1, times 1 over 2 squared, which is 1/4, so it's positive 1/4. If I plug in 3, I get -1 to the 3rd, that's a negative, and then 1 over 2 to the 3rd is 1/8. And what you'll find in this particular sequence is that the sign alternates from negative to positive to negative to positive because the position number is the power on the negative. Every time you hit an even, it'll be positive, and every time you hit an odd, it will be negative. Okay, so I know the 5 is also going to be a negative. And then the 1 over 2 to the n, these are just powers of 2 on the bottom. So 2, 4, 8, the next one will be 16. And then the next one will be 32. And so forth. Okay, so that's not too bad, hopefully. A couple other things that are going to show up when we talk about sequences, and it's going to be the idea of something called a factorial. So a factorial. A factorial is represented by taking a number and using an exclamation point after it. What this basically is that number multiplied by the number 1 less, multiplied by the number 2 less, all the way down till you get to 2 and 1. So it's every positive integer multiplying all the way down to 1. For instance, just a basic one, 5 factorial is simply 5 times 4 times 3 times 2 times 1. Okay, so a factorial is simply the number multiplied by every whole number less than it up to 1, or down to 1, I suppose. Now these numbers get very big, obviously. This one here, 5 times 2 is 10, 4 times 3 is 12, 10 times 12 is 120. So that one's already up to 120. As soon as you get like 10 factorial or 20 factorial, you get very large numbers very quickly with this. Okay. But you will see factorials in your sequences, so you'll need to know how to evaluate those. A couple special factorials. 1 factorial is defined to be 1, and 0 factorial, even though 0 doesn't really have this idea, because you can't multiply by numbers less than 0 that are whole numbers. So we define 0 factorial, and it also is equal to 1. There's a reason we define it that way. It becomes very useful to define it that way, and it follows a pattern as well. But for now, just know that 0 factorial is 1, 1 factorial is 1, and then everything after that is just the product of all the numbers below it. Okay? Your calculators can even do factorials. I just got to find the button. I think it is, I can get rid of all that stuff. I think it is under the math. Is it under math? Under number? Maybe not. No, I'm not even sure where it's at. There it is. It's under probability. So you go to the math menu, hit the math button, and go over here to PRB, probability, I think is what that refers to. And it's the 4th one down. So let me give you a value like 5 factorial, one I just looked at. Hit the 5, hit the math, go over to probability down to 4, and that will give you the 120. So your calculators can do factorial. Hopefully you can find that faster than I just did. Okay. The last thing I want to talk about here is something called a recursive definition. Recursive formula. Basically, that's where you use prior terms. Use prior terms to determine new terms. A very famous example of this is something called the Fibonacci sequence. In the Fibonacci sequence, you take the first term, which would be a sub 1, define it as 1. The second term would be a sub 2, define it as 2. Define that one as 1 also. And then every term after that, we'll call it a sub n, is simply the sum of the previous 2 terms. So a sub n would be a sub n minus 1, that's the previous term, added to a sub n minus 2, which is 2 terms ago. So like for a sub 3 then, that would be, so if the n is 3, then n minus 1 is 2, that'd be a 1, and a sub n minus 2, n minus 2 would be 1, so it'd be a sub 1, which is 1, and you get 2. All right, now if you continue this sequence on, you're just adding the previous 2 terms together. So it starts out with 1, then 2, and then you get 1 plus 2, which is 3, 2 plus 3, which is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and so forth. Okay, so that would be the first 1, 2, 3, 4, 5, 6, 7, 8 terms of the Fibonacci sequence, a very famous sequence in mathematics.